Good evening, one and all. Now we will start our next session with our next expert speaker, Professor Dr. Kaustubh Shedbalkar sir, on topic Introduction to AI and ML in Electric Vehicle Technologies. Before going to start the session, let us have brief introduction about Professor Dr. Kaustubh Shedbalkar. Dr. Kaustubh Shedbalkar is distinguished academician and researcher in electrical engineering with over 15 years of teaching experience under UGC at Shivaji University, Kolhapur, and Dr. Babasaheb Ambedkar Technological University, D. Batu, Lonere. He holds a PhD in electrical engineering from Shivaji University along with an MTech in electrical control system and BE in electrical engineering from Walchand College of Engineering, Sangli. Dr. Shedbalkar has made notable research contributions in including journal and conferences publications, a Springer book chapter, and two published patents currently under review for grant. He has served as a reviewer for IEEE International Conferences and IET National Conferences and was selected for prestigious AICTE Quality Improvement Program QIP for his doctoral research. As principal investigator, he has also received funded research support under the D. Batu VC RPG scheme. His academic leadership extends to university examination roles and invited expert lecture on control system at various institutions. His key research interest includes AI application in renewable energy systems and electric vehicles, making him highly knowledgeable and impactful expert speaker. With this, I would like to invite our speaker, Professor Dr. Kaustubh Shedbalkar sir. Over to you, sir.
Yes, thank you, ma'am.
Yes, sir.
So, good evening, all. Am I audible to all of you?
Yes,
Yes,
sir.
sir, you are audible.
Yeah. Whether my slides are moving, sir?
Yes, sir. It's all fine. You
Yeah.
can start.
So I will start with the session. So before starting of this session, I would like to thank Professor Dr. V.B. Magdum, coordinator of this workshop, and Professor P.S. Magdum to give me opportunity to present in this ATAL FDP on integration of AI and ML for sustainable electric vehicle development and smart mobility. Secondly, I'm very much happy that there are so many active participants in this workshop. In the last session, so many questions were raised by many of the participants. So that is encouraging for the speaker to present the things whatever we are having. So today my topic is related with the introduction of AI and ML, artificial intelligence and machine learning in electric vehicle technologies. So basically we will start with the introduction. The artificial intelligence is rapidly becoming core component of electric vehicle technology. Uh, Further moving, EVs are just beyond a change in propulsion and transforming them into smart, connected, and highly efficient systems. So, the AI is not just improving performance of existing electric vehicles, it's also underlaying the groundwork for future high efficient, connected, and truly intelligent mobilities. So, starting with this note, uh, we will start with the introduction of this section. The first is defining the core. So, basically, to understand the AI role in the EV, we must define what do we mean the artificial intelligence for that particular EV technology. The broader concept of machines being able to carry out tasks in a way that we would consider it smart. So that is the role of AI in the electric vehicles. In EV, this is the main idea that system makes autonomous decisions. So that is the role of AI. And again, ML is the subset of that particular AI technology that allows a system to learn from data rather than going through explicit programming. For example, instead of writing human programs on rule-based conditions for every possible scenario, the ML, the machine learning models or algorithm, watches the millions of miles of driving data to learn how to identify and give the signals. So for that purpose, machine learnings are essentials. So while adding to this note, uh, while considering the AI and ML for the electric vehicle or smart sustainable transportation systems, the main important uh, concern is having that data. So input data for training of particular models in maybe supervised or unsupervised learning models. So most of the data is not available easily, but there are some websites. It is for information to the different participants who have asked the question in the previous question. There is a website called Kaggle. In that, the real-time data is available. It is open source. You can download it and use that data. There are data sets available on NASA website as well as on MIT websites. So you can download that data and use that for your research work as well as for your project related work. So basically, whenever we talk about the electric vehicle, the paradigm shifts from engines to the algorithms. For over a century, the automotive industry was defined by mechanical hardware in terms of pistons, gears, and internal combustions engines. Today, we are witnessing the fundamental shift from the electric vehicle. Now EV is no longer just a car with a battery. It is a software defined vehicle that is called as SDV. As we remove the complexity of the engines, we replace it with the complexity of data. And this is where the artificial intelligence and machine learning become the brain of modern EV. Now, why the AI and ML are required for the EVs? The transition of electric mobility brings unique challenges and traditional challenges that traditional softwares cannot solve. So AI and ML are required for primarily three reasons. So first is managing uncertainty. So unlike the fuel tank, the battery is a living chemical entity. It performance changes based on temperature, age, usage pattern, and n number of different things. The ML is the required to predict the, for example, state of health or state of charge. We will discuss it later. What are those parameters with high precision to prevent drivers from the being stranded or being stopped. Second is solving the range anxiety. As we know, the EVs are having always the range anxiety issue with the owners or with the drivers. The efficiency is the currency or the money of the electric vehicle world. AI optimizes the energy consumption in real time by analyzing traffic, topography, road conditions, weather conditions, so as it starts to complex for standard algorithm to handle dynamically. Third one is processing the big data in the real time. A modern EV generates terabytes of data from the sensors like radar, LiDAR, cameras, uh, throttle position, braking positions, different kinds of temperature sensors are there, positional sensors are used. So that from that we are taking the sensor data. Only the artificial intelligence can process this data fast enough to make split second safety decision in autonomous driving. So here I would like to take an example of Mercedes-Benz S-Class, which is a non-EV segment vehicle. if it runs for 100 miles, approximately 160 kilometers, it will generate almost 1.5 TB of data from that particular sensors, whatever they are installed in that. So it is not an EV, but it is a luxury segment car. Now consider if there is a EV with autonomous driving systems on and other features in that, how much data will be there. So in future, the EV will have the issues related with the big data, or that can be handled by the big data. Which data is to keep with the vehicle and which to flush out or remove from that particular memory will be the upcoming future problems for the EVs. And last point, the brain versus the body. If the battery and motor are the heart and muscle of the EV, AI and ML are the nervous systems. Without this intelligence, an EV is just a silent car. With it, the vehicle becomes proactive partner that predicts when it needs maintenance before the part breakdowns. It optimizes its own charging to save the owner's money, and it adapts its driving style to specific habits of the users. So, at the conclusion of introduction, today the session objective is, today we will like to discuss how the AI is ultimately making electrical mobility sustainable, safe, and scalable. So, for that purpose, we are going to uh, through this session particularly. So this is the AI generated image where the AI engine powering the electric vehicle resolution. AI EV is challenging the unpredictable battery. Unlike the fuel tank, a battery performance changes constantly. That can be done with the AI, that smart battery management. Range anxiety, drivers having fear of being stranded makes maximizing the energy efficiency critical for EV adoption. The dynamic range optimization, the AI can analyze traffic, weather, and terrain conditions in a real time to extend driving ranges. And the data, EV generates terabytes of sensor data that requires split second processing for safety. The real-time autonomous decisions where these data can be used to shift it safely. So basically, we will start with the basic types of electrical vehicle. So these are four basic types of electrical vehicles. First is the battery electric vehicle. So it is solely operated on battery power, resulting in zero emission. The batteries of these type of EVs can be recharged by plugging the vehicles into the charging stations. The BEV present a lower running cost, reduced environmental impact compared to the other types of EVs. Second one is the plug-in hybrid electric vehicle, PHEV. So they have both battery and internal combustion engine, providing additional power when the battery is exhausted. The PHEV can operate in all electric mode for a certain distance before switching to the hybrid mode. When the battery charge uh, reduces or the specific driving condition necessitates it will go to the hybrid mode. In all the electric mode, a vehicle relies on electric power, whereas in the hybrid mode, both battery and internal combustion engines collaborate to propel the vehicle. This adaptability allows to accommodate short journeys emission free and switch to the hybrid mode for more extended trips or journeys, or when the battery capacity is exhausted. However, they are having the higher running cost and carbon emissions compared to the battery electric vehicles. Third type is hybrid electric vehicles. They are equipped with internal combustion engine and an electric motor. The electric motor is powered by battery, recharged through the regenerative braking and the internal combustion engine. Unlike the previous PHEV, these are not typically charged externally. Instead of that, they are charged to the itself by regenerative braking. It is also known as self-sufficient in terms of powers. Hybrid electric vehicle provide enhanced fuel efficiency, lower emission compared with the traditional vehicles. However, they offer lower level of electric drive compared to the previous two methods. So in India, it is called as smart hybrid vehicles. Mostly the Maruti Suzuki vehicles comes under this category. And last one is the fuel cell electric vehicle, FCEV. So FCEV is another type of EV that utilizes hydrogen to generate electricity to power the electric motor. The sole emission from FCEV is water vapor, making them zero emission vehicles. However, these types of EVs are not yet widely available, and the infrastructure for producing and transporting and storing the hydrogen is still in the early stages. So there are some examples I would like to share for battery electric vehicles. The Tesla Model S or the different types of Tesla vehicles, they are completely comes under the category of battery electric vehicle. PHEV, for that Toyota Prime or Chevrolet Volt plug-in hybrid vehicles, they are utilized. Hybrid electric vehicles, Toyota Camry or Honda Accord. These are the two vehicles available in US right now, not in India. The Toyota Camry is available in India with the hybrid electric vehicle. And FCEV, hydrogen-based Toyota Mirai and Hyundai Nexo. These are prototype models that are utilized in the system, or they are utilizing the fuel cell technology. So these are the basic types of EVs. In this slide, we will see the what is the progress or development and adoption of electric vehicles. I have taken this image from one of the IEEE access paper. So in the 1830s, first electric carriage was developed. After that, practically rechargeable EVs are developed. In late 80s, EV gained popularity for urban usage, but in 1912 the gasoline prices were down, and because of that, in 1920 gasoline cars dominated the EV decline. But when after 1960s or 1980s, battery technology improvement was started. After that, the fuel or gasoline prices are go on increasing, and the cost to produce that and the environmental impact were seen. So again, battery technology improvement and interest of researchers and industrialists in the EV technology gain. In 1996, GM launches its first EV, and in late 1990, prototype EV like Toyota RAV4 EV was launched. In 2008, Tesla launched their first vehicle, Roadster. In 2010, Nissan, and in 2016 again, Tesla Model 3 was present. Uh, in 2020, global EV sales were start to increase, and other automakers ramp up their EV production. Right now in 2025, major automotive makers plan to go for all electric by 2035, and it is the fastest growing charging infrastructure present and the fastest growing industry, that is will be the EV segments only. So applications of artificial intelligence in electric vehicle technology. So I have arranged this session in such a way that so there are 5 to 6 major components where AI can be utilized for that particular EV applications. But as whatever I have seen in the schedule, there are so many sessions detailing related with particular one point. For example, tomorrow there is a session on state of charge and state of health prediction and estimation things. So in briefly we will discuss that. But there are some battery management system related estimation or detection is required, like remaining life, useful life estimation, or thermal runaway detection, that are not covered. So we will go in detailing discussion for that particular points. So battery management system, it is the one of the major component or major aspect of electric vehicle in EV from AI point of view. So first is the state of charge estimation. So state of charge estimation is required to know how much range is remaining to recharge it again and again. So accurate state of charge is hard. To estimate accurate state of charge is hard due to non-linear and hysteretic battery dynamics and varying driving conditions and temperature conditions. So there should be algorithms or there should be some mechanism that will give us the continuous state of charge in terms of percentage or in terms of driving range for each of the cell or pack from range estimation and BMS control. Sorry. So for that purpose, we required the input like real-time voltage, current, battery temperature, time. Sometimes the vehicle and environmental variables or conditions are must be known to us and the different data loggers available in the real time. So for that purpose, the researcher have done most research is done on these particular 2 points, SOC and SOH. The recent research work is done on the deep feed forward network, other algorithms like long short-term memory (LSTM), gated recurrent units, convolution neural networks. Some of the research have done used ensemble machine learning algorithms like random forest or gradient boosting for training the data sets and real world data for training and as well as real world data sets. So this particular recent algorithms that are used in real-time vehicle. For example, BMW i3, that is EV, pure EV, in 2024, manufacturing was started. They have used the multimodal driving and driving algorithm for battery features to achieve significant lower errors on estimating the SOCs. SOC, that is the state of charge. So SOC is related with the range and state of charge is related with the how much battery is performing as it compares with the new battery. For example, SOC is having the 80%. That means suppose the range is of 100 kilometers or 1000 kilometers. 80% means it will go to the 800 kilometers for that purpose. And state of health, that means if the battery was new, it will go to the range of 1000 kilometers. The SOH is 80% now. At 100% charging, the battery will go for the 800 kilometers. So that is the difference between SOS, SOC and SOH. So SOH, that is the state of health prediction, is costly to measure directly, and it depends on the complex aging mechanism under the diverse EV usage patterns. So to calculate the SOH or discrete health uh, of that particular battery, to maintain and to take decision when to replace it. For that purpose, we required inputs like historical charging discharging curve, capacity or the energy rates that are utilized by that particular battery, internal resistances of that battery, temperature history, and its fleet telemetry. Temperature history depend it is going to change with respect to seasons as well as with respect to locations. So for that purpose, whenever you are estimating the SOH and considering the temperature history, it should be taken care that if you are using the data set from cold area, that cannot be implemented to the conditions like India. So that data set should contain uh, temperature history from respective regions only. So for this purpose, the algorithms which are utilized mostly the convolution neural network. Second one is the deep neural network and bidirectional long short-term memories. These are three mostly used algorithms. Uh, Other deep architectures with transfer learning or domain adaptation are used between the its cell types. So these are the basic input and output requirements and the algorithms which are utilized. Next one is the remaining useful life RUL estimation. So this is in terms of might be in terms of number of charging cycles or in terms of number of kilometers or number of months or years, the output of that particular estimation. So EV operators need advanced knowledge of how many cycles or years remain before the battery hits end of life limit. Direct experimentation of this particular requirement is too expensive and it is too slow. Uh, if the battery, generally we consider for two-wheeler EVs, the battery life is of 5 years. So experimentation with the real time is slower one, and experimentation is also costlier one. So for that purpose, we require to predict residual cycles or the time to end of life or to full future capacity trajectory. So for that purpose, we require time series of state of health or cycles, number of cycles for charging and discharging. Operating conditions like temperature, depth of discharge are required, and it required features like voltage and impedance curve of that particular battery. So for this type of estimation or prediction, this we will look after few slides in detail also. But for brief, I am telling this. For these type of algorithms, we required temporal convolution neural network, hybrid physical informed neural networks, or ensemble machine learning models like gradient boosting plus bidirectional LSTM for degradation forecasting. For that purpose it is. Next is a thermal runaway detection. So thermal runaway in lithium ion batteries can cause fire. So due to heat, the fire is catch. Early detection from noisy sensor data is difficult, especially under the fast charging and high power operations. So we required a system that gives us a warning in terms of binary or graded warning, or predict time to run away, or to trigger the derating or to shut down. So these types of outputs are required from this for this particular thermal runaway detection. So for this we required inputs or the data set which contains high rate temperature sensors, voltage or and current of that particular battery or cell, uh, pressure or smoke detector indicator in that particular, and plus the operating mode, which in which operating mode the motor the battery is, it is in charging or discharging mode. So for that purpose we are utilizing clustering algorithms like k-means or supervised classifiers or hybrid data driven models plus electrothermal models embedded in the battery management systems. So a combined K-mean plus K-means algorithm plus thermal model scheme for EV batteries reported a very good results for early warning of that particular thermal runaway conditions. Last point is related with the cell balancing. So cell balancing, if there are cells which are manufactured, basically the batteries are manufactured with different uh, manufacturing units. There are variations in the cell uh, packaging. A non-uniform aging causes cell to cell change in voltage or mismatch in the voltage, changes in the state of charge. It reduces the usable capacity and accelerating the degradation if it is not properly optimally balanced in that case. So we have to take control action and selection of cells for charge and discharge condition. We have to balance the current, and time to time we have to equalize the state of charge while minimizing the energy losses and its wear. For that purpose, we required inputs like SOC estimation, uh, per cell, what is the voltage in that particular pack, temperature, internal resistance, pack with having current or operating modes like charging and discharging. For that purpose, reinforcement learning algorithms are used or supervised machine learning controllers are used. In some cases, uh, optimization with augmented AI are utilized, but I have not gone through that detail in that particular augmented AI. But reinforcement learning and supervised machine learning are mostly utilized in case of cell balancing technique. Second part, that is with the autonomous driving and advanced driver assistance system, that is called as, in simple words, ADAS. So there are 6 levels of ADAS from level 0 to level 6. Level 0 has zero automation. Level 1 has basic driving assistance. For example, cruise control is there. In level 2, partial automation like automatic parking, acceleration, deacceleration, and steering control. So in India right now, level 2 ADAS is present in Mahindra vehicles, or that newly launched 2-3 vehicles are there from Mahindra. It is having the ADAS level 2. The level 3 conditional automation, which includes multiple drive assistance feature and AI integration. Level 4 is the high automation, whether in that it is capable of complete self-driving, geo-reinforcement, and required human input for some conditions. And level 5 is the highest level of ADAS, whether full automation is done, no human intervention allowed, no steering and paddle control is required. So for that purpose, these 6 levels of ADAS are utilized. So in ADAS system, first point where AI can be utilized, real-time decision making. So EVs must choose optimal speed. Uh, Whatever I'm telling now, these are the separate areas: optimal speed, lane changing, power split under varying traffic conditions. So these are different areas where decision making is required. Real time decision making is required. Lane keeping, there is a separate section known as lane keeping assistance system, LKAS. Uh, so for that purpose, we require real time decision making. Uh, Real-time control actions such as accelerating or deaccelerating or braking, lane changing decisions, and powertrain set of points. We require to predict these outputs. We require inputs like vehicle states, for example, speed, acceleration, environmental inputs like traffic, signal, road slopes, and road conditions. Sometimes the energy demand from the battery should be known. So for this purpose, uh, the researchers have used deep reinforcement learning algorithms, multi-agent reinforcement learning algorithm, and deep neural network for the prediction of real-time decision making. Second one is the adaptive features. So adaptive features like the fixed energy management or comfort for that EV cannot cope up with the changing driving style, traffic, or weather conditions, leading to suboptimal range and user experience. So for that, features like adaptive adjustment of torque limit, heat ventilation and cooling usage, regenerative braking strength, charging strategies to keep efficiency and comfort balanced with that particular EV. So for that purpose, we required inputs like, or the data set should contain high resolution telemetry like battery status, energy consumption, what are the different driving patterns, what is the ambient temperature required, and route conditions. So if we know that, we can go for the deep learning models or deep reinforcement learning models, or some research have worked on the online learning, fuzzy logic, or an ANFIS and FIS based systems for that particular purpose. Next is the driving pattern analysis. So energy uses strongly depends upon driver behavior. If it is so aggressive or so defensive. So like many of the cars are having the mode like for example, eco mode is there, city mode is there, sports mode is there. So different driving patterns are given by that particular electric vehicle, which is hard to quantify without automated analysis of large telematics data sets. So for that purpose, we have to predict or estimate uh, cluster or labels for driving style. That means eco mode or normal or aggressive or sports mode, whatever that modes are there, and the features used for uh, further control or feedback for acceleration as well as for braking. So for that purpose, we required inputs like time series of speed, acceleration, throttle position, braking events, how many braking events are there. Sometimes location and traffic are required for that particular purpose. Again, for this type of forecasting or prediction analysis, we require clustering or classical machine learning based algorithms like SVM, random forest, logistic regression, or deep learning model like LSTM and BiLSTMs are utilized. Next one is the personalized energy recommendations. So for that, eco driving tips are ignored by choosing individual routes. So personalized energy consumption, that means in an optimized way, we are going to the endpoint or the desired location with the optimum energy. So eco driving modes are available uh, that gives the individual routes, but the driving, the rider or the owner or driver of that particular vehicle so many times ignores that because of its habits and vehicle conditions, limiting the achievable, and it affects on the achievable saving and range extension. So personalized suggestions while running that particular EV on that particular route, there are requirements of personalized suggestions such as recommended route, cruising speed, departure times, charging times, or in-drive information through the messages are required. So for that purpose, user-specific driving history must be known to us. Preferred routes are known to us. Driving habits or acceleration, deceleration habits should be known to us. Contextual data like at which time of day you are traveling from that route. If it is in morning, afternoon, or evening, what are the traffic conditions that should be known to us. For that purpose, again, supervised learning for consumption prediction, for example, gradient boosting, DNN are utilized. Some of the cases, DRL for personalized driving experiences are utilized. It is based on self-aware driving recommendations. So if the owner is same or the driver or rider is same for the one car, so the AI will understand its habits and tendency to how he drives the vehicle. So personalized messaging can be done. And last one is the eco driving assistance. So drivers rarely maintain energy optimal acceleration and speed profiles. Real-time assistance is needed to extend EV range and reduce emissions. So for that purpose, we required eco speed profiles, or when to accelerate or when to brake, or we required the direct control trajectory for minimum energy usage. So for that purpose, we required instantaneous speed, road condition, traffic signaling, and sometimes upcoming route geometry are required. So again, for this purpose of prediction or estimation, a deep learning based trajectory planning, or RL based reinforcement learning based eco driving controls are utilized. In some cases, hierarchical reinforcement learning is utilized. So next area where in the EV where AI can be utilized, it's smart energy management and range optimization. So vehicle traffic and climate data is required to optimize routing, braking, energy recovery, and heat ventilation HVAC operations in EV through learned models rather than fixed rules. So first one is the predictive route planning. So classic shortest path routing ignores the energy usage. Generally, what happens if we set the end location or the desired location at particular EV, it gives the shortest path, but it generally ignores the energy usage, traffic conditions, gradients, and charging constraint. So EV may face range anxiety, or it may require longer time or longer distance trips for completion of that particular task. So our requirement is energy optimal or cost optimal route should be there. So often with predicted travel time and remaining state of charge along the path, we can estimate the predictive route. So for that purpose, we must know the road network, elevation on that road, real-time traffic conditions, charging station locations, and EV state, like how much energy is available or state of charge is available for that particular purpose. But on the larger scale, this type of route planning is not uh, generally success in large scale. Uh, in related with the small area, it can be done or it can be successful right now. So for that purpose, we required machine learning, energy consumption predictors, uh, algorithms like neural network, gradient boosting, or quantile regression neural network models that can be combined with the optimization, like spectral clustering algorithms. Likewise, we can combine. So for that purpose, we required. Next one is the regenerative braking. Uh, the regenerative braking is used or required to charge the batteries itself. So fixed braking does not fully recover the potential, but it may harm the comfort and safety under the varying traffic conditions or the road conditions. So we have to uh, calculate the optimal split between regenerative and frictional braking. Every time frictional braking is not possible, every time regenerative braking is not possible. So braking torque command and energy recovered from that particular we have to calculate. So for that purpose, we required the information like what is the speed of that vehicle, deacceleration demand, uh, what is the deacceleration demand, distance to lead the vehicle, road slope, vehicle slip, battery state of charge. Sometimes traffic light uh, are required, traffic conditions or phases are required. So these are inputs should known to us. From that we can go for this type of regenerative predicting output, where to when to apply the frictional braking and regenerative braking. For that purpose, or the research have presented reinforcement learning like Q learning, DQN, neural network controllers, fuzzy logic, and genetic and combination of genetic and PSO optimizers are utilized. Last one is the climate control. So one of the largest auxiliary load in the EV is climate control in that particular car. So conventional PID controller are underperforming in case of harsh climatic conditions generally. So we have to optimize the compressor speed, fan levels, wall positions. In very few EVs, heat pumps are utilized to maintain the comfort with minimum energy. So for that purpose, we must have the knowledge of cabin temperature. So what is the set point, ambient temperature, humidity outside that particular area, passenger occupancy, how much is there, whether the battery or motor uh, is heated or not. That particular point we must have to know. So for that purpose, model predictive control with learn different learn models are utilized, or reinforcement learning for energy saving HVAC controls are utilized. So next sector where the EV AI can be utilized in case of EVs, that is charging infrastructure and grid integration. So in that, load balancing is there, dynamic pricing, charging demand forecasting, optimal charger scheduling, and fast charging control. So EV charging with the grid by learning from historical and real-time data to obtain optimize load, price, and charging schedules while protecting the infrastructure and its use comfortably. So in load balancing, uncontrolled EV charging creates local peaks where transformer overloading is possible or voltage drop in the distribution networks are possible. To overcome this, we have to allocate optimally the charging power across the stations and time slots for flattened demand and respective network limits. So for this type of work, we must know the inputs or the data, that is real-time station loads, charging station loads, grid constraints. What are the grid constraints in local grids? EV connection states. For example, what is the arrival? Like there are many apps in which you can book a slot for EV charging stations. So at what time you are arriving, what is the state of charge of that particular EV while arriving, uh, how much amount of energy is required for to charge that particular vehicle, and renewable energy forecast. So many of the charging stations are majorly dependent upon the renewable energy. So that forecast must be known. So for that purpose, supervised machine learning models are mainly utilized to predict the load balancing conditions, to predict the uh, optimal charging power across the stations. So reinforcement learning or optimized allocation of power is done by using multi-agent reinforcement learning or graph-based reinforcement learning. So next is dynamic pricing. So static tariffs cannot steer electric vehicle users away from peaks and causing congestions and high grid cost. So we required time varying or time changing prices for the charging, or a personalized tariff that align user incentive with grid needs. So for that purpose, we must know the electrical prices, transformer loading in that particular area, weather forecast, renewable energy forecast, and charging behavior at that particular charging station or that particular EV. So for that purpose, regression analysis are generally utilized for demand elasticity, deep neural networks for demand prediction, and mixed integer optimization or the reinforcement for setting optimal prices. These different sectors are having different algorithms that are utilized. Next is the charging demand forecast. So grid operators need to know the accurate short-term and medium-term forecast of EV charging load to plan generation, its reserves and infrastructure. So for that, predicting charging power requirements or energy per station or per unit of that charging station or in that particular region or horizon uh, for time duration from minutes to the hours conditions. Generally, 1 day ahead requirements are 1 day ahead scheduling is required for this type of demand forecastings. So for that, we must know the historical station load, uh, weather and traffic patterns should be known, EV adoption trend in that particular area, some spatial correlation among the stations should be known, and the information like whether it is a holiday or working day, that should be known, because depending upon that the scheduling must be done. So for that purpose, the basic algorithms utilized are convolution, LSTM, deep learning models like all the range of LSTM, by LSTM, uh, convolution LSTM, regular LSTMs are utilized. Ensemble models are utilized like XGBoost or light GBM models, and hybrid models are utilized like GAN plus LSTM for low quality of data is available. So next is the optimal charging, uh, optimal charge scheduling. Scheduling many EV with different arrival times, state of charge, and limits of grid or transformer is complex combinational task. So it is the most difficult part for optimal charge scheduling. So we must have to predict, or we must have the start time of charging, charging rates, what is the charging rate, the sequencing decisions for each EV to minimize the cost. It should have not charging in terms of peak at the time of peak load, or there should be no delay at low loads. That should be known to us. So for that purpose, we required the inputs like EV arrival and departure times, energy required, current state of charge, the station charging station power limits, grid constraints or transformer overloading constraints are there in that particular area, and sometimes dynamic pricings are also required. For that purpose, deep reinforcement learning algorithms utilized. Some have used the attention-based DRLs. Multi-agent reinforcement algorithms are available. Hybrid approaches combining machine learning forecast with mixed integer programming are available. Last one is the fast charging control. So everyone requires that the vehicle should be charged within the minimum time. So for that purpose, high power fast charging is utilized. It can cause the voltage sag and battery degradation if current and power are not carefully managed. So adaptive fast charging profiles and time varying power limits that balances the speed of charging as well as grid impact and battery health that must be controlled. So for that purpose, we required the profile, battery profile in terms of voltage and current limits, charger ratings in terms of kilowatt, grid constraint, and temperature at that particular uh, battery or state of charge of that particular battery. Again, for that purpose, the model predictive control for real-time control of fast chargers is utilized, or supervised machine learning algorithms are utilized for that particular purpose. The last area that is having more focus on in AI for EV, the predictive maintenance. The system monitors the health of components like main components of EV like drivetrain, motors, electrical system, altering drives, or fleet management to potentially uh, issues, which reduces the unexpected breakdowns and costly repairs. The traditional maintenance misses early or loses the early detection or degradation of the problems or the issues in terms of motor, inverter, powertrain components, causing unexpected breakdowns and high repair costs for EV electric vehicle. So component level health indicators should be there that will check the fault its classes like severity level, on temperature level or different levels, and remaining useful life estimation along with alert to drivers uh, so that maintenance action can be done properly. So for that purpose, multi-sensor data like vibration sensors are there, current and voltage sensors are there, temperature, speed, torque. Some of the high-end vehicles are having fault codes. If there is blink on the dashboard, that fault code will be read that by particular software interfacing with hardware. So it will give the fault code and historical maintenance log captured by that particular vehicle. So that can be done. So in this again, the vibration analysis is a different area or prediction on the basis of vibration. Motor faults can be done. It is another area where AI can be again utilized. The algorithms which are utilized are mostly random forest, support vector machine algorithms, gradient boost algorithms are utilized for battery particular batteries particular predictive maintenance. The thermal management, thermal sensor data and vibration data is utilized mostly. So for that purpose, hybrid physical informed or digital twin models are utilized in that particular case. So these are the basic core areas which are used where AI can be used in the electric vehicles. So in that, I have skipped many of the detailing because in upcoming sessions we are going to discuss about it. So which are not discussed in case of these 5 days, I will discuss that only with again briefly because 20 minutes are remaining. Remaining useful life prediction. In case of lithium ion batteries, they are renowned for their high energy density, low cost, low self discharge, and sustainability across the various applications. So remaining useful life RUL prediction in case of lithium ion batteries plays a crucial role in battery management system. Uh, Safety assurance and the anticipation of maintenance need for reliable electric vehicle operation. So again, I have told you that there are three different concepts. SOC is different, SOH is different, and RUL is different. So RUL is remaining useful life. In that case, how many charging or discharging cycles are remaining to complete its end of life for that particular battery, or how many kilometers or miles range that is remaining that can be predicted, or for how many years or months that battery can be utilized, that is predicted from remaining useful life predictions. So I have taken this flow chart or a chart where the RUL prediction is classified. So one is the model based predictive. In that, electrochemical models are from electrochemical models the prediction is done. Another way is filtering model. In that, Kalman filter and particle filters are used. Kalman filters, uh, as we know, it is frequently utilized for filtering technique in predicting the remaining useful lives of battery. It is an estimator that utilizes the system model and series of measurements to determine the state of the system. So for in that way, the Kalman filter are utilized. Again, uh, extended Kalman filter and other parts of that can be utilized for the estimation. Particle filtering, it is the idea generated from the Monte Carlo approach, which is the popular filtering technique that used in prediction of lithium-ion battery remaining life. This method uses a set of particles to estimate the probability distribution of a system state. This represents many alternative system states and their corresponding weights, which are modified at each time step depending upon the fresh sensor measurement. It is capable of dealing with non-linear and non-Gaussian systems, making it suited or very suitable for the RUL prediction. This approach, unlike the Kalman filter, does not require detailed system model, but it finds number of uh, it is difficult to find number of particles uh, for the computation purpose. Next type is the data-driven uh, method. Uh, Stochastic techniques like Gaussian process and linear process. Next part is related with the artificial intelligence. In that, ANN, artificial neural network, uh, is utilized. So an ANN can have numerous layers, each of the each of which contains multiple neurons and nodes. A logistic regression is used to calculate the value of each neuron in a given layer based on the value of all neurons in the previous layers. In that way, the ANN is utilized. Second one is the SVM, support vector machine. It is a supervised learning algorithm that can be utilized for regression and classification application. So SVM can be used to develop model that predicts the remaining useful life of lithium ion battery based on feature extracted from the battery operating data. The this remaining life prediction for batteries is crucial for battery management systems as well as for data mining technologies in improving ability to estimate the remaining life. The classic single radial bias kernel functions utilizes utilized by the SVM has poor generalization and can result in inaccurate RUL predictions. So next is the RVM. RVM is the relevance vector machine. It is similar to the SVM. The RVM uses the Bayesian approach to calculate the necessary weights for computation. This technique is characterized by high degree of sparsity and it can make predictions based on probability. So next part is with the deep learning models. So deep learning neural networks, DNN, uh, are used for prediction of a kind of machine learning approach that employs multiple layers of artificial neurons to identify its pattern and relationship in the data on the health and degradation of lithium-ion batteries, and performs operations such as convolutions on multiple activations in a single neuron. For a battery remaining life prediction, various DNNs are based on recurrent neural networks, including the LSTM or GRU models. These models are widely utilized. In next one is the gated recurrent unit. Another commonly used uh, algorithm in the recurrent neural network is GRU, which is usually used to predict the sequence such as uh, remaining life prediction. Compared to the more complex LSTM, the GRUs offers lower computational cost, which has contributed to its widespread usage in the studies involving time-based data. It has given that capacity and predict the remaining life that relies on the data such as voltage, temperature, current. We have seen the inputs required for that particular purpose. Next is the fusion-based model. In that fusion-based model, uh, fusion of data driven with EKF, that is combination of EKF, not sorry, KF, Kalman filter, and data utilized fusion of data with filtering, particle filtering algorithm. And last one is the data driven fusion with the uh, data actually available. So these are the challenges and issues with the remaining life estimation. First one is the thermal runaway and temperature rise, overreaching or over discharging, internal short circuit or internal damages. We have to develop a smart advanced thermal management system. Battery material issues, uh, different manufacturers organizing uses different battery materials. There is no standard specifications generally. Solution general approach including composite formation, doing coating and encapsulation, electrolyte modification and control to maintain and enhance the performance of material. Battery cell balancing issues are there. Battery aging and relaxation issues are there. So where the AI actually utilized, this is the fifth point, training algorithms issues for the RUL. Because of the complex electrochemical and dynamic environment, developing battery model is very difficult. So it is not possible to function under the dynamic load circumstances. So we have to develop enhanced thermoelectric model for optimal charging, energy loss, and temperature rise. So that is the one of the application of AI that can be utilized. So next part is related with the optimization of charging of EVs. So there are two basically EV charging strategies. First is the uncoordinated charging. Uh, it refers to random charging behavior where the EV owner can charge their vehicles at any type of charging station at any time as they prefer. The problem with uncoordinated charging is that it can lead to overload transformers, power outages, and increase electricity cost. Moreover, it can result in battery degradation and shortened battery lifespan due to frequent charging and discharging. So option is coordinated charging. So in coordinated charging, it involves uh, planning and managed charging scheme that are applicable to optimize and manage the EV charging operations, such as mitigating the grid stress, enhancing the energy efficiency, and minimizing the cost. These schemes are also uh, consider various factors in their management. For example, renewable energy availability, electrical demand, user preference. These are generally considered. The coordinated scheme can be implemented using two types of charging system. First one is the centralized scheme and second one is the decentralized scheme. So this is the generalized architecture of centralized and decentralized. In the centralized structure, there is one single aggregator, central aggregator, and in decentralized, as per the charging station, aggregators are different. So a centralized entity that coordinates the charging of EV within a specific geographical area, such as a city or a town. The central entity in this charging station, known as aggregator, communicate with both EV user and the grid operator. It obtains the transmit demand as well as performs system configuration and coordinates other operations. To achieve this, the aggregator first collects the charging information from EV owners, such as the identity, number of EVs, EV battery capacity, state of charge, arrival time at charging station, etc. Then it executes an algorithm to optimize the charging schedule based on the collected data by taking into account overall power demand and electricity prices in the market. The aggregator submits these schemes to the grid operator for approval. From the perspective of business model, the aggregator and the grid operator are regarded as independent of each other, but they are cooperating entities. The role of grid operator is crucial, and the operator should ensure that adopted scheme aligns with the stability and efficiency of the power grid, considering factors such as grid load, peak demand, and balance between supply and demand. To keep this balance, uh, the grid operator may execute some kind of admission control for new charging requests based on the current grid status. If a charging schedule scheme is not acceptable, the grid operator will reply to aggregator to revise the schedule or wait until the grid resources conditions allow the execute the scheme. So with such approach, the negotiation process would be involved, and consequently complexity of the overall process goes on increasing. So in decentralized charging approach, an incentive-based strategy is introduced. Again, it is a optimization related uh, problem where incentives can be given. An incentive-based strategy that introduces where charging schedules of EV are affected indirectly by electricity price. The EV owners plays an active role in making their charging decisions utilizing information provided by the aggregator, such as current electricity prices and availability of charging station in the area that is managed by that particular aggregator. The primary objective uh, of the adjusting electricity price is to motivate EV users to charge their vehicles during off-peak loads or off-peak hours, thereby reducing the load on the grid during the periods of high demand, similar to the centralized approach. Each aggregator collects user information or event, predicts the charging demand for the next period of time, inform it to the optimal charging scheme. It cooperates with the grid operator and align the charging prices with the condition of the electricity market. The status of power grid is considered while doing all these things. As a result, the pricing strategy, the EV owners make a charging schedule based on their personal preferences, aiming to minimize the charging cost. So these are the two different methods. So there are classical optimization techniques for EV charging. First one is the linear programming. It stands out as a widely employed optimization technique. It formulates a problem model as a linear set of equation and aims at optimization, where both objective function and constraints are there to linearity. This characteristics is algebraic and applies to both problem and algorithm. So linear programming has been proved to be the effective in optimizing charging schedules that encompasses multiple EV and multiple charging stations and power grids. Next one is the dynamic programming. The dynamic program is widely used optimization technique in mathematical and computer science for solving complex optimization problem. However, no standard mathematical formulation for the dynamic programming problem is exist. Instead, it involves problem solving method where the problem is decomposed into smaller sub problems and solved recursively. It leverages the fact that optimal solution to these sub problems contribute effectively resolving the larger problem. It worth noting that dynamic programming can be equivalently formulated as a linear programming. As a result, the linear programming can serve as efficient alternative to the functional equations approach in solving the problem, whereas the dynamic programming helps to characterize the polyhedral combination, structure of discrete optimization problem. Additionally, it ensures the global optimality for solution in general nonlinear optimization problems with convex constraint. It is particularly well suited for dynamic systems such as optimizing charging schedules involving multiple uh, EVs and charging stations, where the charging rates of each EV may vary over the time. Last one is heuristic algorithm. Uh, these are employed for approximate methods to find solutions for complex problems, especially when the problem is too large or too complex. These algorithms have been proven beneficial in the addressing charging schedule problems. There are few examples which includes the PSO or GA or ACO and colony optimization, where these type of methods are utilized. These are the generalized method. So applying machine learning for EV charging optimization is again a separate point in which the supervised learning, these algorithms are firstly trained using the labeled data sets. Particularly, they are effective in scenarios where historical data are available. The various supervised machine algorithms like SVM, NB, K nearest KNN, or neural network, random forest, these are utilized. The random forest is an ensemble method that relies on multiple decision trees. According to that, the algorithms are selected. In unsupervised learning algorithm, algorithm makes decision without requiring labeled data to train the model. The unsupervised learning algorithms autonomously identify the pattern and structure in umbrella, in big data structures with unlabeled data without human supervision. These algorithms groups the database on similarities or differences, useful in applications like customer segmentation, or algorithms like unlabeled data separation or similarities finding. The unsupervised learning algorithms also comes with drawback, such as these algorithms complexity and the potential for predicting faulty output when it utilizes the unlabeled data. These algorithms are applicable to identify suitable EV charging scheme, and these types of algorithms are particularly useful in scenario where the availability of historical labeled data is not obtainable or unobtainable. Next is the semi-supervised learning models. In that, it integrates the concept of both supervised and unsupervised learning. It offers various benefit for EV charging scheme uh, optimization, including forecasting energy demand, applying dynamic pricing model to manage the demand and grid load, and the predicting strategies for station placements. The semi-supervised learning may also provide personalized charging recommendations to the EV owners, such as suggestions suggest the best time for charging, location of charger, etc. And the reinforcement learning, it involves learning from past experience and improves the performance through a trial and error correction approach. Unlike the other learning algorithms, they rely on initial training data. It explores the various options, aiming to refine itself with each iteration. With each iteration, so it can be instrumental in implementing demand response strategies. The reinforcement learning algorithm can learn to adjust the charging rates or suggest the charging time to the EV owners based on grid conditions, promoting energy conservation during the peak hours. It can also be adopted to develop algorithms that schedule charging times for EVs in a way that minimizes the grid stress or maximizes the cost efficiency. Next is the deep learning algorithm. So these are rare concept of neural network which compromises interconnected nodes, neurons that are arranged into multiple layers. The input layer manages the input data, hidden layers uncover the pattern within the data, and the output layer presents the results. Uh, these algorithms are generally used for uh, generally the algorithms are LSTM, GNN, GRU, RNN, and ANN models. Deep reinforcement learning, last parameter is or last point, whether it combines the RL and DL, reinforcement learning and deep learning, to take benefits to solve the complex problems, while RL, reinforcement learning part, defines the objective. The DRL component offers the problem solving mechanism. So these are used for exe to applicability in the EV charging optimizations. There are studies going on in this particular area for fast charging stations particularly. So this is the summary of different algorithms, their application in EV charging, their advantages, limitations, and computational. We have mostly discussed the last part of that particular machine learning technique. Next is the, as already 9. So we will fastly go through this decision making and planning for autonomous vehicle. Decision making and planning are the core aspects of autonomous driving system. These factors are crucial for improving safety, driving experience, travel efficiency, and all that purpose. The behavioral prediction of traffic participants in terms of machine learning based behavioral prediction, probabilistic model behavior prediction, and mixed method behavior prediction. So this is the overall uh, structure or the different layers of autonomous driving systems. So there are three layers where AI can be implemented. First is the behavior prediction. This is the A part. B is the behavioral decision making. C is the path planning. In these three cases, the AI can be utilized. And last one is the end-to-end decision making and path planning layer. So for these four layers or four sectors where the AI can be utilized for autonomous systems. So one by one we will go. So within short time, I will cover behavioral prediction of traffic participants. In that, it can be done by machine learning model, probabilistic model, and hybrid model. In machine learning, mostly utilizes the decision tree, support vector machines, and deep learning. In again deep learning, RNN is utilized. Again, RNN has many algorithms like LSTM, GRU, bidirectional RNN, multi-layer RNN, attention mechanisms. Nowadays, attention mechanisms are having more papers or research work is going on that. Convolution neural network is the part of that. Second one is the behavioral decision making. In that, it is done by the three methods: classification, reactive decision making, linear decision making, and interactive decision making. In linear learning decision making, reinforcement learning, support vector mechanism, machine, deep reinforcement learning, and incorporate optimization theory. These are utilized. Others, like in some cases, decision tree or fuzzy logics are utilized. Bayesian network or Markovi decision makings are utilized in the reactive decision making. So path planning. In path planning, most famous is the graph algorithms. That first Dijkstra algorithm, that is the very famous algorithm for path planning. Second one is the sampling method, RRT and PRM. And last one is the numerical methods. In that, MPC, model predictive control, is well suited for the AI applications for that. So last part of the today's session is AI powered electric routing. A key focus is multi-constant optimization that simultaneously manages state of charge, waiting time, tariff conditioning, energy consumption, and charging needs. So while planning an electric vehicle route, so these contents should be known to us: state of charge, waiting time, traffic conditions, energy consumption, and charging needs of that particular system. So algorithms for routing have changed to accommodate EVs in particular needs. Modern pathfinding algorithms take into account variables like battery capacity, energy usage, sorry, availability of charging station, whereas earlier algorithms only consider the quickest path, while sorry, while vehicles may move as efficiently as possible without running the risk of battery drain, thanks to the energy efficient routing methods. So these are the basic 5 challenges in EV routing. First one is the EV route feasibility concern, battery limitations, charging station availability, and waiting time. Fourth is the cyber security, and someone has asked the cyber related cyber security that comes under the EV routing challenges, uh, data privacy in electric vehicle. So basically, cyber security comes in the picture when they are with the autonomous vehicles mostly. When they are, if there are two or three autonomous vehicles going simultaneously, then cyber security majorly plays the role in that particular case. Fifth one is the powertrain efficiency and thermal management. So AI-based approach is having for EV routing. The first one is the reinforcement learning based, that Q learning is utilized. So Q learning and SAR-SA are the value-based reinforcement learning method that are used for traffic aware EV routing. So in that, uh, it the SAR-SA, the SARS updates the value based on policy action section selection, improving the stability of stochastic algorithms. Markov decision process, it in that EV route is modeled as the decision process as defined by the mathematical formulation of that particular equation. Third one is the multi-agent uh, reinforcement learning. In that, interacting agents, rendering it with suitable uh, conditions for optimizing electric vehicle routing in dynamic contents. The MARL, that is multi-agent reinforcement learning, facilitates collaboration and rivalry among the electric vehicles to improve traffic flow and energy efficiency. Again, there are subtypes like centralized training with decentralized execution, cooperative and competitive MARL, graph-based MARL for EV routing. And next part is related with the machine learning based algorithms. Again, in that, supervised and unsupervised. In supervised machine learning, uh, support vector machines for traffic prediction, neural network for travel time and energy estimation. These are the two types. And in unsupervised learning and charging station placement, it plays a role where K means clustering for charging station placement. DB scan, it is a very famous density based spatial clustering of applications with noise. DB scan is useful for dynamically identifying the high traffic zones without requiring predefined number of clusters. So DB scan defines the cluster as region of high density separated by the region of low density. And that principle they have worked. So last point, that is with the optimization of powertrain and thermal management in case of AI or by using AI. In that, there are three main parts. First one is the AI powered motor and power electronics optimization. The machine learning based energy loss prediction that can be done through the CNN LSTM. These are the areas just I'm discussing. Second is AI optimized semiconductor switching. Uh, Someone has asked how the AI is utilized in the power electronics. AI agent, augmented predictive maintenance, AI based, digital twins and transformers based applications are there. Second one is the AI enabled thermal management. In that, uh, physics informed neural network, PINN, for heat flow analysis is done for thermal management. RL, reinforcement learning based adaptive cooling, that is deep Q networks are utilized. AI controlled battery thermal protection, in that CNN and electromechanical models are utilized. Last one is the AI driven uh, regenerative braking optimization. In that, RL based predictive braking control, AI based road and driver analysis, And last one is federated learning for adaptive regenerative braking that can be addressed by using the AIML in that particular. For these presentations, I have used these 8 generalized papers. Most of them are review papers taken from IEEE and elsewhere. So thank you for your patience listening. Now I will stop the sharing of my. So if anyone is having questions,
Hello, sir. In the chat box, one question is there. Is battery
Ah.
charging optimization is a part of BMS?
yes, battery charging, that means cell balancing can be there, and battery charging is a part of BMS. Yes, definitely it is a part of BMS.
Okay, sir. Any question from participant? Please unmute. Okay.
Sir, good evening, sir. Hello.
Yes, sir. Yes, sir.
Good evening, sir. It was an excellent session. One question I have. By using thermal runaway detection system, can we use 2 batteries in parallel? If one battery, by using thermal runaway, we are able to detect the condition of battery. If the condition of battery is not working proper, is not good, can the system will automatically move to the second battery if we use in parallel?
So there are two things, sir. First, uh, if there are 2 cells or 2 battery packs are there,
Yes, sir.
then the thermal runaway basically works for the heating of that particular battery. If that battery is
Yes, sir.
heated, for that purpose, we can switch to the second battery and we can run on that system.
Okay. So you have explained my doubts were there when you were giving presentation, but my
Okay.
doubts were solved by that slide. Thank you so much.
Okay. Okay. Okay.
Thank you, sir. Thank you.
Any question?
I think there is one question from Jayashree ma'am. What is the industry state of art of AI and ML for EVs? So, in India, the highest state of art EV that uses the AI and ML, that is the Mahindra EVs that recently launched. And across the globe, if we talk about the Tesla cars, that are state of art EVs that are using the AI and ML.
Any question?
Any questions?
Okay, madam. Please continue.
Okay, sir. Thank you. Thank you, Professor Dr. Kaustubh Shedbalkar, sir, for such an insightful session on Introduction to AI and ML in Electric Vehicle and Technology. Thank you, sir, for sharing your knowledge. Thank you. Now
Thank you,
I
ma'am. Thank you.
announce today's session is over. Thank you all the participants for joining. Thank
Before
you.
leaving, switch on your cameras first. Okay, for photo. Magun sir, please allow.
Possible turn on your camera.
All participants, please turn on your cameras.
Okay, thank you. Thank you very much.
Thank you.
Thank you all.
Thank you.
Can we exit, sir?
Yes, 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 please.
Thank you.
Mogum sir, unmute. Mogum sir, please unmute yourself.
Okay.
Any suggestions? Any suggestion? No, na?
Okay. So today's sessions are over here. Tomorrow, day 2, session number 3 will start at 6 p.m. So you are requested to join 10 minutes before 6 p.m. tomorrow. Thank you. Thank you, one and all.